Well, hello and welcome. My name is Peter Tuddenham, past president of ISSS, and I'm here with Len Tronale, who is also past president of ISSS, and he's going to repeat a workshop he gave at the recent ISSS 2019 annual meeting and conference in Corvallis entitled Several Systems Education Experiments. So it's almost a 2-hour workshop, and we'll have questions at the end. So thank you, Len, for doing this, and over to you.
Well, thank you, Peter, for giving me the opportunity to do this because only one person made it to this evening session on systems education. But I know that the ISSS people, as well as a lot of other people, are interested in systems education. And so I'm describing 4 major experiments, but I'm only going to go through the first one in this first case because it takes too long to do the others. So I'm going to try to get through why we call these experiments anyway in systems education. And I'm going to go through the pilot offerings of ISGE, the Stealth System Science for Every University. It's 124 slides, so I'll be happy if I even get through that in 2 hours. It'll emphasize the assessment data for these courses over 5 years of offering, the test for efficacy and student acceptance, and the review of a multitude of special teaching and learning features used in ISGE that could be called computer-assisted instruction in the future for them. I'm not going to go through the University of California, San Diego course on unbroken sequence of origins that occurred in 1985. There were 17 guest speakers for that. Some of them were Nobel laureates. It was very big examination of what I call the unbroken sequence of systems origins, or USSO, is a spin-off of my systems processes theory and the theory of emergence. These talks will be converted to YouTube for a course I'm giving right now that's completely online, Systems Engineering 5100. And then I'm going to look at that engineering graduate course as another experiment, Introduction to Systems Science, although I've taught it not only for systems engineers, but for master's program for sustainability experts too. It's now being offered completely online, and I'll offer in the second part of this series 7 slides on that. But perhaps the most important thing for ISSS ingenues to learn is what we did in the past in terms of systems education, because I hear a lot of current interest, but we've done 50 years of examination of systems education and efforts at it, and I have 9 reports to report to you about systems education and systems research. And then in the end, the very end of the second session, I'll do conclusions, lessons learned from and for the future in terms of systems education. Now, before I start why I'm calling these experiments, I'd like to mention to you that this is a series of talks which I declare as fair use because I'm using lots of pictures which are not always copyright released, and essentially this is meant as a presentation and talk for this limited number of 5 or 6 people in ISSS who've joined us today, as well as for my 22 students in systems engineering. So it's a one-to-many, like as if I was using overheads in the classroom, and so I call this fair use. So please, if you're looking at this, do not use any parts of it because it is not copyright released under a federal law. Why do I call these experiments? The definition of experiment in this context, or in usual context, is a procedure carried out to support, refute, or validate a hypothesis. Involves repeatability, analysis, controls, collection, and analysis of data. And we're going to go through a lot of data in this one. In this context, our hypothesis is that teaching systems is more fundamental and useful than the current methods of teaching. It features past attempts. We're still trying to get it right. Usually in the past, we learned in ISSS that only a center or institute, not really a line unit, a regular department, and that was usually externally funded, so very dependent on funding, was offering systems education. It did not come as one of the programs in chemistry, biology, geology, or in business and so on. It also was dependent on student demand and graduation. And learning from past mistakes, I'm doing what the systems engineers have taught me to do, bluffing at the beginning, where bluff, B-L-U-F in capital letters, means the bottom line up front. The death signal for most systems education programs in the past, and this is up front, was a change in administration. A president retired, a dean retired, a chair retired who was sponsoring the systems education program, and it was actually eliminated after that. Examples are the president of the University of Louisville, who was our own James G. Miller, one of the early presidents and who I consider a co-founder of general systems research. So from the outset, one has to prepare for the legacy. And I use my own Institute for Advanced System Studies, which we called IAS, because otherwise the acronym would be the number one S, which would not be good. As an example, I did not prepare for my retiring, and so they eliminated that institute as soon as I retired. Surviving experiments are State University of New York's PhD program, which is CLEAR's program, and Portland State University, which is interdisciplinary, with Martin Swick, Wayne Wakeland, Lindstone, and George Landaris, and others, who have been very active in the ISSS in the past, but aren't active too now. So why are we calling these 4 experiments? Because they're attempts at systems education, and we can assess what happened to them. So the experiment 1 is integrated science general education. That's the only thing I'm going to go through today. And it's essentially stealth system science for every university. Oh, that's cute. Why do I use stealth? Because we have stealth aircraft and you can't detect them, right? It's because I portrayed system science not as system science. That's why we call it stealth. I kind of put one over by using other means called integration mainly, and synthesis and unification as the realm of system science, such that they then maybe didn't even know they were getting system science. Recently, the ISSS has rediscovered this issue of systems education, but there seems to be no institutional memory. The former ISGSR and the new ISSS worked on systems education for many decades, and in my humble opinion, many former lessons learned have been forgotten and they need to be revisited and implemented. Otherwise, systems education's poor history will be repeated over and over again. That is what the first 2 hours of this talk are all about. Lessons learned from the past, 4 experiments in systems education. So let's go through this first experiment, integrated science general education. We're going to go through the courseware goals, purpose, objective, the basic idea of it, and how it solves general education programs across the university. So it does a role, it performs a function, it solves a problem for many universities across the country and internationally. The course organization, its components and workload per week, exceptional levels of diverse funding in the millions. And I might say I was the first one in ISSS to get large grants of millions of dollars for doing essentially system science. How ISGE achieves synthesis, integration, and unification, which should be of great interest to systems people, because that's what they do too. The test pilot offerings, what the test population was like, what the test instruments were like, the real assessment data, the grades achieved, the likability by the students, and then added things like the unique new transdisciplinary labs and skill practice. We'll also go over unique courseware innovations, and I'll illustrate them for you in about 30 videos, which is more than 250 megabytes of stuff. I'll go over 9 inbuilt features that enhance systems-based transdisciplinary teaching and learning. I'll go over 7 special multimedia features, and I'll illustrate and present to you 7 trademarkable features, which means they're so unique to our program they should be trademarked. Case studies will be presented also to show the depth and rigor not only of GST, but the depth and rigor that is possible for an interdisciplinary course and courseware. And the reason for this is that it has had a bad name all the years, the 50 years I've been in universities. Interdisciplinary has been a bad name because all the funding goes to the disciplines and the departments. We're going to be not anti-discipline. We build on the disciplines to show cross-disciplinary important features. We'll look at practicalities of ISGE development and of marketing and dissemination. So I'm going to look at the basics of whether this is livable or not. And then at the end, I'll go through some basic conclusions and problems with ISGE as caveats. So let's begin with goals, purposes, and objectives. The need for the product. Every college student must take 4 courses in science to graduate. This is usually the general education requirements in the United States and hopefully internationally. This product completely satisfies that requirement. It's all the GE in one place. So science general education is about 10% of every student's college requirement to get their degree. And believe me, they're very dedicated to getting their degrees. But what is the outcome? Science literacy is extremely low in the United States compared to other developed nations, extremely low. And this drives an intense search for workable alternatives. Our data shows ISGE is one alternative. So we're looking for the deepest level and detail of new knowledge and problems, and we want to include fundamentals like the scientific method and applications simultaneously. So the basic idea is a revolution. Teach science using general systems, not disciplines. So this is what ISSS, I think, would be very happy with, and the former ISG are, as unifying the sciences. To get integrated science, though, you need a revolution in science content, in learning methodology, as well as application and dissemination to get bought or to get adopted. We also include bridging art and science and unifying nature and humanity by diligent application to student lives. And one of my last videos will show that. So the beginning of ISGE is a revolution in content integration. So its principal goal is construct a unique learning environment through computer-assisted instruction for all non-science students to achieve a deep understanding of the scientific method and the most important theories and mechanisms of astronomy, physics, chemistry, geology, biology, computer science, and mathematics. So that includes the physical sciences, the living sciences, and what you might call the symbolic sciences. Integrated and presented not by discipline, but by common features across the disciplines. That's what we term isomorphies and learning themes, so we don't scare away the non-systems people. Learning themes, integrative themes. This turns the conventional presentation mode upside down. It maintains and respects the integrity and rigor of each science, but it requires synthesis at the most fundamental level from the very beginning to the very end. And it builds in, as I'm going to illustrate, some 30 aids to help students learn. So systems, STEM really means science, technology, engineering, mathematics, all via systems education. Well, the basic idea is DE teaches the sciences as separate, isolated topics at the present time. So if you look in the upper blue left corner, you see they take a course in biological sciences, maybe they take a course in oceanography, they take maybe one other course in computer science. They often miss chemistry and the other ones altogether because they're taught as isolated topics. And those are taught by disciplinary people. That means they don't even look at the other sciences when they're taught. I know because I've taught a lot of those in biology. But ISGE is exactly the opposite. It's unified, integrated. It's more like the upper right-hand corner where you're teaching the common processes across all of those sciences, which are different colored spheres. So you look first at the basic fundamental isomorphies as integrative themes. But I've also been sensitive to the fact that general education has a problem as a nation because we're not doing very well in it. So here's our first animations or videos that I created with the the support of National Science Foundation. Let's see if they work. I'll show 30 animations in this talk if the tech gods allow. That's our early and first video that all the students did for every module. And if you look at it again, I don't know if you can see it, but it starts with, oh, it won't do it again. Okay. Here we go. Now it'll do it again. It starts with, as in large, so in small. It has a base, galaxies, and the large galaxies are beginning in a simple, and it emphasizes what we do in the instant. Look at this diagram. It's got two things at the time. It has fans going outward, which is variation, and yet the arrowheads are going inward. So its emphasis is integration. And this is the Institute for Advanced System Studies symbol, and the NSF symbol, and the Cal Poly symbol. Okay? So that also is used in the various talks. Wow, my first animation worked. Happiness. I hope you saw it. So basically for ISGE, 4 revolutions are needed. The first one is a significant integration of content. ISG completely reorganizes the science curriculum and sequence. It simplifies, compacts, and reinforces. And when you stop and think of it, this is one of the 4 first objectives for the ISSS as a society. You need the integration with that, though, of new teaching and learning methods like multimedia, competency-based progress, personal tutoring, cooperative learning, hybrid teaching, active discovery learning. We've thrown all of those in. It also has new assessment tools, which we made up to test whether we were getting a point over. And it's an experiment in role. There's real-life production problem solving, entrepreneurial stimulus, and mentorship, as well as solving problems for the world and the species. Now, one of the things we tried to do is to program design promises to NSF to solve these 20 specific general education problems. So in addition to these, I mean, each one of these is actually an active button in our computerized demonstration from these. This is not a poor international scores, poor integration, lifelong science, better dissemination, cover the scientific method more, use multimedia strength. All of these needs more connections, poor cumulative effect. All of these are GE problems. But this button went to a similar type slide that showed exactly the other problems for interdisciplinary teaching and learning. And what we attempted to do is these also were buttons in the 20 obstacles. I didn't bring that one up, but I don't know if you can read that. In the middle box, it says ISGE learning feature number 5, graphics and graphics-based games and exercise. It answers all of these at the same time. So there were all kinds of solutions built into the teaching and learning methodology. So I can't click on these because this is not an active screen, but it was for my demonstrations that I gave to 120 different countries. Here's another one. Automated links, connections, and bridges answered all of these problems simultaneously. So if you put in all the features that we had, we answered a lot of the problems with general education, as well as the problems that students get into when they're trying to learn a new idea. So we solved, in this case, 15 problems simultaneously with just 4 learning features. So the solution had a synergy built into it. It was easier and more efficient to solve several related problems simultaneously with one solution that was designed, a systems education solution, then attack each separately. The synergy of effort and the synergy of benefit. Modern systems research supports this comprehensive strategy. You can only replace an established system with a much more efficient system. This is from the hypercycle research of Nobel laureate Manfred Eigen and one of our key systems sources. So that took care of ISGE goals and objectives. I hope you got the message. Now let's look at the course strategy and structure. And by learning one thing, learn many. Because you're learning about a system, there are many instances of systems in the universe and in the world of man and of nature. And so by learning one thing, learn many. By understanding one thing, understand many. By solving one problem, solve many. And so we've built that into the courseware. There is a YouTube already after the first year of trying to do research on ISGE, and it has that URL right there. You can go to it. And it was produced on campus. But also, this came from Peter Tuddenham, who's sponsoring this. The new science standards have a lot of cross-cutting concepts. This was a federal document offered in 2018. This is some 30 years or 40 years after I started ISGE. But they finally caught up because almost one for one, it's the same as the intents of nature's enduring patterns, which was the theme, part of the theme, and literacy for the ISSS 19 and for the ISGE. You can see patterns, cause and effect systems and systems models, scale, energy and matter. You'll see structure and function, cycles, feedback, evolution, stability, hierarchy. You'll see all of those as themes in ISGE. So it both emphasizes the patterns and the systems focus, because ISG is based on the natural sciences and because it is basically system science. The main difference is in causes, and we propose isomorphies are the causes or the mechanisms that we can learn in great detail. They're algorithms on how nature and human systems work, and that's why we're teaching them. Notice both ISG and the Nature's Enduring Patterns book have many more patterns to follow, way beyond these from the current science standards, but at least it's consistent with the science standards, and they finally caught up with us, I would have to say. So the focus is on not on disciplines, but on SP3T, we call it generally, and the P3 because I emphasize processes, Peter emphasizes patterns, and so does ISSS, but we're both emphasizing pathologies lately, as stimulated by the systems engineers. So what we look at first is isomorphies across phenomena of all 7 basic sciences. And there's no sight of this in conventional general education. They don't teach it at all, period. Nothing. Even though the science standards are now saying that we should do that in elementary school, there's nothing in college. It requires abstracting the system's process models. And this is an amalgam of several slides I generally use. Artificial computer DNA that's interacting with proteins on another scale entirely, the quarks and so on in the nucleons of an atom, and the nucleus of an atom, or a cell. When you look at them and abstract on how they work well in nature, and something the size of a galaxy, which is huge compared to all of these things give us hints. It turns out they have the same dynamics. So entities is widely different, and different scales, different parts, different times of origin, different mechanics of origin. You can still see the universal processes or algorithms when you abstract to the general level, how they came into being rather than the scale-dominated disciplines. How did we ever get in this situation? Well, humans just broke up the universe around them. I mean, remember, we used to think the Earth was flat, right? Some people still think that. And early observations were not adequate. But as science has progressed, we've gone back in time billions of years, and we've conceived of a much wider thing than humanity alone. But that requires, all of it requires abstract modeling. And we're not too good at that as a species to begin with. So the curriculum would take a full academic year, would satisfy all the science GE requirements just to be of use to the universities and colleges throughout the United States and elsewhere. But it would present revolutionary knowledge organization and technology. They're very busy week assignments, a wide variety of learning methodologies. Sorry, there's repetition there. Um, so these would be the integrative themes, and you notice that all of them are isomorphies. And we would first go through hierarchy and teach them about hierarchy and what to see when you look at the world in order to see a hierarchy. Then we'd show common hierarchies that exist throughout the 7 sciences. So in that, you're going through all the science requirements, in fact, more than the usual requirements. And the weak requirements are at least a couple of multimedia modules, but I add a number of human things in here, these 3 here, which were face-to-face. But we'll see that all that has gone away, as well as interdisciplinary labs. So it was quite a taxing week for the students. We also enjoyed exceptional diverse funding, at least over $2 million spent on general systems theory. Can you believe that? So we were successful in getting grants, but we got grants from a lot of places. From my own university, about 4% of the 2 million. Other campuses, 11%. The state, the chancellor system, of all the 23 campuses in the California State University, about 10%. And then we got additional 30 from federal and from foundations, 45%. Although these did not really participate in producing the problem, producing the program. I'm essentially a producer in that case. And at the end, we'll talk about prospects for the future. So this is where the money went. First of all, I had my institute fellows. We had 30 to 35 from different disciplines, and a lot of them were scientists, and they would meet with me on release time. We would spend money so that they would be bought away from their courses. As experts in astronomy, physics, chemistry, geology, I was already in biology, so there was no release for that. I just donated my time all the time. And I got others from computer science and mathematics. I want to talk about my fellow in geology and computer science. Both of them were very, very helpful throughout this project. They're all retired now. But the largest part of the budget went to student computer scientists. They were mostly undergrads, some grads, some actually became professional staff who I actually paid their full salary for. They were from our own computer science and computer information systems departments. The former is in the College of Science. This is in the College of Business. And then some additional students who are artists. Altogether, about 125 of them. And some graduated to related jobs at prestigious institutions like Jet Propulsion Labs or Caltech. So they were doing this kind of like an internship together with supporting their college education while they were taking courses. The hardware was a problem, but the schools, a lot of that $2 million went to buying the computers. So we had microcomputers in an ISGE lab and a dedicated ISGE lab before they threw me out of it. Now that's no longer necessary. Every undergraduate has their own laptops and uses the internet to distribute the software. The software we used was AuthorWare Professional and various other graphics softwares. I might say that this was one of the big problems because NSF liked my project so much that several other projects were funded by NSF in education that used AuthorWare Professional. But then it was bought out by a bigger company, and that was bought out by a still bigger company, and it had a rival software, and AuthorWare Professional no longer exists. So the whole second NSF grant was me reprogramming all that stuff that AuthorWare Professional businesses did in order so that we had it on something like C++ or Java. Then there was, of course, the secretary managers and work on filing and so on in order to get the thing done. So this is the critical question for you guys, I think. How does ISGE accomplish synthesis, integration, and unification, which is one of the goals of the ISSS? First of all, it does it by the integrative themes, which are general systems isomorphies. There's no place else that one teaches isomorphies at the depth that we do in ISGE, I mean. By their very nature, they're integrative because they're descriptions of universals that are common mechanisms across all the sciences. But we don't use just isomorphies. We also blend in links. Links are similarities between phenomena within a science, like those that exhibit the foundation for genetics for traits in ecosystems, or cycles in photosynthesis and animal metabolism. Both of those are in biology, but they have commonalities. Connections were similarities between phenomena in different sciences. So across things like hypercycles in society and biochemistry, or in chemistry and biology. So that's a connection between sciences. But one of the most fascinating ones for those who are artistic minded were the bridges between natural systems and human systems. And I'll bring this up when I talk about the ATP and origins of money, or between the genetic code and music in terms of hierarchy of sequences. Lots of not insignificant, actually very, very significant similarities between human systems and natural systems that most people get nowhere else. Then there were domain integrators we concentrated on, like continental drift unifies much of geology, or genetics explains much of biology. I spent 50 years of my life, or 40 years, teaching the basic course in genetics, from cell molecular to ecological, in my department of biology. So I'll not go over these former slides that talk about these things now, but basically you see here that the ISGE knowledge base was a bunch of interconnections between the isomorphies, and this is what led to the linkage propositions. The integrating theme was the presentation of a systems mechanism, and then illustrating it in the 7 sciences by case studies in the phenomena. So we were showing the integration across all of these things. So it was accomplished in ISGE by 5 different methods: isomorphies, links, connections, bridges, and domain integrators. So it wasn't nonsense. We were really doing SUI or throughout the year in all the case studies. Links, connections within one science, connections between 2 sciences, and bridges between sciences and the arts. For example, there are 2 shown here. For example, this is a hierarchy, this is a hierarchy, but we showed that genetic code, computer code, music, and languages, these are the arts, music and human things, all can be broken down into hierarchies, and so in fact have similarities. And later on I'll show you this transformation from the ATP molecule to the coins and economies in humans as essentially evolution of humans and evolution in the cell coming up with the same answer for a problem in both. Amazing and impressive. So there are multiple methods of synthesis, integration, and unification throughout the entire year. And the knowledge base that was feeding the ISG was an e-web of these connections. And one could search through all the links, connections, or bridges in many ways. For example, you could ask it, well, if it was fully developed, we would have been able to ask it, give me all the cases of similarities between astronomy and biology. Or it's 12 modules in scientific method. We use the scientific method as an integrative theme too. Math and statistics also is an integrative theme. Everything connected. And this, we were on the quarter system at that time, and so we had 5 multimedia modules on the scientific method, like practical applications, models of science and interpretation, tricks of the trade, impact on your personal life, history of key discoveries. I'll show you some slides on that. 7 steps in the process, origins and history, how it's used differently in different disciplines, and it is integration versus reductionism as a general problem, tools and instrumentation, science and the eternal questions, limits of science, values and ethics in science, women in science. Science is one way to know of a spectrum of ways of knowing. So a whole lot on the scientific method. So ISGE was very science-based, and it should be, because it was a general education tool for uh, accomplishing general education in science, right? We also looked at the scientific method as a history of people. Take, for example, these people that are shown in here, starting with probably Anaximander and then going all the way through Newton uh, and all the way to Pasteur. Um, Many of these were before the thing you might call the Nobel laureates. So let's walk through one or two of the systems themes to see how it's integrative. Okay, this is relative to the assessment data. It's unusual for GE. Nearly 60% of the students were upper class. In the 90s, that might be much less. But let's just look at, in this case, boundaries. These are all case studies, the causes of hurricanes and tornadoes, boundaries in them. Um, actually, seawater buffering, El Nino and La Nina cycles. This is not hierarchies. This is a number of different things. Network interactions in land, sea, and air. That might be interesting to you, Peter Tuddenham, as we're engaging in ocean literacy. Earth and atmospheric stratification, geomorphic cycles, feedbacks in geomorphic cycles, and so on. So there was a lot of science that was learned in this by integrating it. We'll demo only two examples, hierarchies and cycles, and that's what these pictures are here. First, we teach the features to identify. So this is the identifying features of hierarchy, and each one of these is a button by which they go through explanations of subsumption and nesting or self-organizing or self-similarity as an example of hierarchies. Then we go through real examples. Let's say we went through hierarchies and we looked at structural hierarchies, idea hierarchies, and so on, which we're going to show you in just a minute. But this is a picture of fractals. It's fractals across biology, physics, geology, chemistry, computer science, and biology. All of those are fractal structures. So first we teach them how to recognize fractals, what the identifying features and functions are, especially functions, because that's important to systemness and its survival. And then we would show them the examples across the sciences. And so we would follow with lots of science phenomena and information. For instance, in hierarchical structures here, we're showing the hierarchical structure of biology. And here, the hierarchical structure of ideas in physics. And here, the hierarchical structure of computers. And here, the hierarchical structures in astronomy. Each one of these, incidentally, was a button that the student could choose to pick this one or that one or this one and the series of them in order to get knowledge about them, because each button would come up with, and it would start off with like case studies of hierarchy in the biological sciences or case studies of hierarchy in the chemical sciences and so on. And by the time the student finished, of course, they would get, why is the computer not going here? Oh, okay. There were built-in pedagogical helps, and this was the pedagogical help stepwise refinement. We would go from the muscle that they could see in their arm, their biceps, to what it was composed of at the next level of hierarchy, down and down and down, all the way to the actin-myosin fibrils. I'll show you an animation of that later on that helped them understand how the muscle contracts. Or we can another example of stepwise refinement was the chromosome. And in this case, several levels. The chromosome is shown as an organization of proteins that organized DNA loops. And the DNA was found to be coiled around 8 nucleosome proteins. And so they got down to the nucleosome level. And here they got down to the actin-myosin level and how the action here caused the action there, how the action here and structure here caused the condensation of the genes. So a tremendous amount of detail was given to them. Here's another one where the student controls the stepwise refinement. They're first presented with a picture of their small intestines, then they click on it and it gives them this one, and they can get an explanation of what they're looking at and then close that one. And then they could click on any on an explanation, in this case, of a magnification of that, and then a further magnification that showed crypt cells and how the volume of surface within their gut was expanded by the folding and folding and foldings that were hierarchical stepwise refinement. So this all allowed them to establish their own pace, to make choices, and to explore following their curiosity. Here's more case studies in hierarchy. Every one of these was a button, and whenever you clicked on one, it gave you additional information and talked about that scalar level of that hierarchy, in this case in chemistry. But there weren't just lessons from hierarchies in natural sciences, there are also lessons for human sciences. For example, we often lately have been arguing for network organization of corporations and network organization of politics, and there's a reason for that. But we tried to show that networks and hierarchies are actually transformable. This is a transformation of a hierarchy into of a network into a hierarchical scalar level thing. And so they are interchangeable to some degree. And animations like that explain we could look over the whole political history of the world and the civilization of the last 10,000 years, where sometimes we had autocrats like we do now, and sometimes we had kings, and sometimes we had despots, and sometimes which were very hierarchical, and that religion is still very much like that. But we can show that they are transformable into certain types of networks. And so it took a long time to evolve back to the democracies of the early Greeks, but it's still a battle, isn't it? Because we still have democracies and despot situations all over the world. So here's looking at cycles, and look at all the different cycles, logic circuit cycles, the cell cycle, organism life cycles, gravity collapse and rotation, Milankovitch ice age cycles, and the sunspot cycles, stellar life cycles, geomorphic cycles. You get the idea. You can cover a lot of science while you're doing the integration. And we continue with cycling as an integrative theme. We could teach features of the systems process first. For example, what to look for in cycles, stages, and a sequence that's required, obligate sequence. Then the specifics of a key science, like the life cycle of a star. In one picture here, it shows our star as it was forming. We're about right here, so we have a long way to party yet before it becomes a red giant and we're wiped out. So first you do get the identifying features, and then you find them in instantiations at the scale of a star and a planetary system, or at the scale of a cell. This is the various stages in the cell cycle. And then teach them about each one. In this case, this was a guide, and they could click on any phase in the cell cycle, and it would explain what was happening in those, as well as those we can't see, like interphase. So a great deal of science was covered, once again, while we were integrating things. And because they are cycles with stages, these things are on the algorithm stage the same thing, because they break down to these abstract isomorphic features. Okay? I might add that all of these were actually pictures that were in the modules. And let's see, we just went over cycles and hierarchy up here and cycles down here. But there are a lot of other modules that could be made to illustrate these things, but we, of course, didn't get through all of those. There can be a dozen more. In this case, you have organized by the disciplines various phenomena in science that you can study from the point of view of one or another of the isomorphic integrators or integrative themes. So there are lots of core ideas across each of the 7 disciplines. Okay, what about the tests? What happened when we did this? Well, we had test offerings, 7 offerings of this of the pilot for this course. at 3 different CSU campuses, and they're shown as the big dots on the right there. And there were 5 at California State Polytechnic University, which is a Southern California one at Cal State Monterey Bay by invitation, which is in the middle, and 3 sections all together at once at the Sonoma State one in the north. So it's quite a distribution across the California State University system, of which we have 23 campuses now. And you can see there's a lot more campuses that could adopt it. So the students on the test population, there were nearly 200 students in the sample, and we're going to go through what their sex, ethnicity, and what their characteristics are in the following slides. For example, there were more females than males when you look at the sex in the sample. About half of them were Caucasian, and this was in the 90s. Nowadays, we have many more minorities than we did in the 90s at Cal Poly. We probably have 3/4 that are non-Caucasian. Females usually take less science and don't like science, and the same thing goes for people who are what we would call not Caucasian. But about half of them in both cases, or more than half, were from those groups. In terms of the student audience, when we look at majors, a lot of them you can see were pre-credential. And let me explain that. They were students who were studying to be teachers. This is a multiplier effect and was good for NSF arguments, because what we were teaching was students who were going to become teachers. So one of my students, actually it was from biology, became a high school teacher, and he continued to teach my stuff that I had taught him and is now about to retire. And he's been teaching it ever since then as an integrative thing to help the students. Let me say another thing about these pre-credential, pre-teacher people, which were 60, almost 70% of the class. One of my professors in biology became the director of the pre-credential program, and he used to send me what he called science phobes, people who left science until the very last thing to take for them to earn a bachelor's degree to become a teacher. They hated science and disliked it. So I was getting the worst of possible groups, you might say, because of that. But it turned out to be a good test of whether this was good science to learn. So nearly 70% were pre-teachers, and that director told me they were about 25% of them were science phobes. Let me go back to that, because language. Nowadays, the English as a second language group will be much bigger, because in the 90s, it was a smaller group. In terms of class standing, you see that many of them were seniors because they had put off science to the last minute because they were science phobes. And in terms of computer usage, daily was very small compared to what it would be nowadays, but that was because it was the 80s and 90s. 92% were working at the same time they were going to school, which is typical of the California State University system. So that's really, our CPP students are lower middle class, and that's why they have to work to get through school. So what instruments do we use? We made up a 30-query pre-attitude and post-attitude survey instrument, which tested whether they liked science or liked multimedia or liked using computers before or after the course. But we also had an evaluation of the learning experiments, and we used a Likert scale of 1 to 7. Why? Because the middle of 1 to 7 is 3, and then it has 3 things on either side, which follow our usual way of describing things: good, better, best, worse, worser, worst, right? So that's why we did that. And we asked 111 questions. I had people complain that the evaluations were too detailed, but we wanted to get some information. And about 100 students were in the sample of 4 class sections from 2 campuses, or 20,000 responses over a 3-year period. And this is an old slide, actually. Student grades were determined by lots of requirements, as you can see here. 4 lab reports, 10 knowledge maps, 4 skill training reports, 150-point midterms and finals, 35 computerized quizzes. It was very rigorous. I don't know why this isn't working. Okay, so data on assessment. These are the grades. 8 pilots were offered, 6 times at Cal Poly and at the other places. A total of 174 students are represented in this data. 80% were pre-teaching credential people. Half were minorities. About 30% were English as a second language. That disagrees with some of my other slides, but it's a more updated one. This is from the NSF report on this, the last one. There were many non-science, science, math, phobe. Attrition was very low, 1 to 6%. 90% work time. Even though 90% were working part-time, attrition was only 1 to 6%. Student achievement was great. 75% earned A's on 900 challenge points of very great diversity. You can see from the parentheses there. 33% were in each category. On the student assessment, 111 questions, the grand mode was 6 on a Likert scale of 7. So they liked it. 31 of 100 were much better than. 99% of the features were better than conventional courses. So that's pretty good results. The post-course course scores for 19 attitudes towards STEM, pre and post tests are showed in other places. The grading challenge was, as you could see, all of these 900 points. It showed how much was involved in the game quizzes, the exams, and the final exam, and the knowledge map. So students were grading on a high diversity of points and a lot of points for 10 to 15 weeks. If you look at what we were testing in those 900 points, some were short-term, some were long-term memory, some were written, and some were activities and discussion. So we covered the whole picture of place. And as you can see there, 34% were A's and 38% B's. So there were more B's than A's, but altogether, that's 72% got A's and B's. For science phobes, that's really good. And when we look at the evaluation statistics at a glance, I tried to put some of the questions down here, but when you have 101, there's too many to put on the chart. But you can see here on the Likert scale of 1 to 7, they were way up there at 6 in many cases and 5. And this was the same as conventional courses, better than conventional courses, much better than, very much better than conventional courses. So they seem to 5, 6 better than conventional courses. And this was a later one. The central tendencies, you can look at means, you can look at mode, but we think that mode is better than means because of the effect of outliers. Let's say you like somebody you pissed off and doesn't like you at all, they can really give you a very low or a very high score because they love you. And those outliers should not be as affecting, but they can affect the mean, but they can't affect the mode. And in this case, for 111 questions, the most usual value is 6, which out of 7 is just about the highest, much better than conventional courses. And then I don't have time to go through all of this. It's too much data for you. And we're approaching our first hour. So I might actually, Peter, get through both of them in this one thing, which would be good for you, I think. It would simplify things. So in this particular case is the before and after scores, and it shows, oh, I didn't add the quotations here, but it shows what it shows is that some things they didn't like as much afterwards, and this is pre and post attitude. You see, they didn't like the details as much because I gave a lot of details in this course, but they liked the visuals a whole lot, and they liked the GE regulations in their college, and they liked science in general before versus after, and technology in general. But they didn't like practicing skills very much or solving problems or the text that went along with the pictures, um, and broadening the education in general. I didn't ask the question about systems here, of course, because that would have given away our um, stealth system science. You can't call it stealth if you're not being stealthy. Okay, this is the mean scores, not the mode scores, comparing the score with their age. We did this in order to see, well, does it change much as they get older? And as you can see, there's more chatter when they get older, but it's not too much different between the oldest age and the youngest age. And then what about their grades? Let's say they got an A, they really liked it, but actually people who were in the F group and the D group almost scored it the same as these are the 111 questions, as the people who got better grades. So you would think the higher grade people would give much more approval of the material. So then we did the same thing, but looking at modes, and you saw essentially the same thing, more chatter as they got older, but basically it was just about within the same one or two categories, as you can see here, with whether they got a good grade or not in terms of their evaluation. So overall, ISGE was superior for science phobes to conventional courses. There's a danger of, I can't remember what it's called, the Thompson effect here, and I noted that in my NSF results, to be honest. There have been studies that showed that when a person spent a lot of time looking at a production line, for example, and seeing whether people liked it or not, just the action of paying attention to their feelings really gave them a higher evaluation score. So that may be what's happening here, because we clearly were trying to serve them. But the mean of the student evaluating question was 6, meaning courseware was much better than conventional, but the mode was 7, meaning very much better than, for 62 out of 101 of the questions. But there's always the problem of the scale and the number of questions. I like the Likert scale. I think it justified the use of the Likert scale. There are always caveats to assessments, of course. Some are not statistically based. Although there are a small number of D and F grades, 70% earned A and Bs. Did that influence them? Individual faculty science stated that they probably could not pass the written midterm, probably because it was interdisciplinary. And so we couldn't measure that, but we did measure this, and you might be interested in this. We gave the final to several graduate students in biology. Since I was department chair of biology at that time, I could do that. And you know what happened? They got the same score as our ISGE undergraduate students. The same score. They didn't do entirely better. Now, graduate students in biology have already taken several courses for their GE requirements in physics, physical sciences, and mathematics, and so they should have done much better than our students. On the other hand, as caveats, remember these were specific questions to this material, and so that's maybe why they just did the same. Students ranked both summary questions. Now, at our university, these two summary questions are the ones that are looked at for you getting advanced to associate professor and full professor. I would recommend this course to a friend. Overall, I'd like to see more courses, both science and non-science, that use these modules and this hybrid learning methodology. And the mean for that, not the mode, the mean was 6.6 out of 7. So that, since it's the most important two questions, really shows a good result. These measures rank primarily students' self-evaluation of learning. Of course, scores were lower for younger students. I even got 3 grants from my local university to improve the evaluations. But both we and NSF kind of were pleased with our results. Now we get into the special features, 7A, B, and C. This is the prettiness of this inbuilt learning aids to enhance teaching and learning. I'm going to talk about LA. Now, learning aids, I covered a bunch of them in synthesis, integration, and unification section already. So we'll start with learning aids. We'll start with this stepwise refinement. I already explained the breaking down of the hierarchy of muscle and the hierarchy of chromosomes to help understand organelles in the cell and organs in the body. So I won't go through them one. But we had another thing called games. Two examples here are the top right is a mahjong game for learning log sizes. And the students would play these over and over again until they got it. So you were supposed to match asteroids and planets and things to a scale or clusters of stars or the walls of a galaxy in the overall universe or a whole organism with the approximate size it was in meters. And this one here said, if I am at the level, hierarchical level of DNA and coming out of a virus, it's actually not necessarily DNA, it's a bacteriophage and not a virus anyway. Where is my cursor? What happened to my cursor? Oh, well, I can't point to that middle one in the left-hand picture. Oh, there it is. The other one is a drag and drop. So what would be the size directly the level below this one or above this one? And you'd have to pull it down. And if you pull down the wrong one, it would reject it. And so you could learn that way. So the computer automatically kept scores play by play for later analysis. But as quizzes, what these were doing is they were the students playing games. So they would play these games for a long time. And as a result, they would learn the material better. And we call that, when we talked about it as a learning aid, we call that time on task. And one of the problems in current education is time on task, and this increased it. Also, e-games dramatically increased the learning. Both male and female like to play games. Numerous embedded games were there for each topic, and all of them were randomly generated. So that thing I just showed you about, it wasn't always the bacteriophage, it was any of the other levels in the hierarchy that we studied, and what was the level below and above and so on, what was its size. Many studies show students need much more time, much more study time. Actually, most of the time we see that in the current technology and stuff, it distracts them from learning. But these attractive e-games actually extended their learning time. And so learning. Also repetition with variety, because it was randomly placed, enhances the understanding. It makes the drill repetition, which is necessary for learning, much more tangibly useful. We also required knowledge maps. Whoops. These are actual knowledge maps that students built on the hierarchy of elements or atoms in the various hierarchy of biological polymers. And this one was hierarchies in terms of the generality of the principles. These embedded quizzes gave immediate feedback. So here was an image, and it was of the Ordovician, and the student had to drag the Ordovician, whether it was part of this, or this era. These are periods. So we're testing whether they had figured out what periods were in each era by the end of this. This is the control. These are the controls here. In this case, they were presented with various of that elements you saw on the last knowledge map, and whether it was part of the gene or part of the protein, and therefore they were learning about genes and proteins. Here's another one of our videos. So basically, we were saying to the students, look, what we're doing is transferring neural nets from our brains as the teacher brains to your brains. And I usually included in there the statement, notice that the student brain is much bigger and smarter than the teacher brains. in this case, and they got a kick out of that. But of course, that was just to show something. So we tried to follow the neurobiological foundations of teaching and learning to describe how to students how hard it is to form a physically new neural net or a new idea. And this is a problem that we feel is very important to instruct students on how hard it is to learn and how hard it is to unlearn. And we use this is what we were saying. Look, you're forming new neural nets in order to learn a new concept. You have to learn a new definition and relate it to all the old definitions. And so that requires physiologically you to set up these neural nets in your brain, and that's very, very hard. But we also showed them that part of learning is to unlearn, and that's very hard too. Let me describe a Harvard graduate's example. We're just past an hour now. I compliment you all, if anybody is still out there, on your perseverance, but hopefully these are pretty things which are, well, let me describe the Harvard graduate's example. There was a video that was made some years ago at graduation of Harvard students. Now, Harvard gets the best students, right? The most smartest and so on. And they asked this question of the Harvard graduates, already determining that because of their curriculum programs and what degree they had earned, that they had gone through the exemplary teachings of science on this following question. Why are there seasons? Wow, what a simple question, huh? And all of the Harvard graduates got it wrong, even though they had been already taught that it was the tilting of the earth that caused the different seasons. That's why Australia has, summer when we have winter and vice versa. And they were all said to the interviewer, it was because the earth got closer to the sun and further out based on the orbit. And that's wrong. And so even though they had gone through Harvard and had gone through the courses, they hadn't unlearned what they thought of as a simple explanation in the beginning. So unlearning is difficult too. And that's part of learning, we say in science. The other thing was learning aid was interactivity. Here's a detail of a neuron for the neural net. And every flag there is an interactive thing. They can click on it and get more information about that part, like the nucleus or the neurotubules that go down the axon and so on. So interactivity was a big part of this, breaking apart major diagrams in order to understand them. All case studies were highly interactive. They were not just page-turning actions. Students were asked to choose their pathway through the knowledge. So there were many thousands of pathways possible for different students in the modules once they were finished. Students were more engaged when they are allowed to and prompted to discover knowledge. They follow their curiosity. They have many choices, they feel, and direct experience, and so 100% retention. 14 experiments in higher education showed consistently that high multimedia interactivity leads to more effective teaching and learning than passive. But Peter has appeared, and it's 1 hour and 5 minutes. What's up?
No, it's all right. Nothing, sorry.
Keep going, huh? Okay. I thought you were going to tell me. Cut it off.
No, sorry. No, had a small carry on. It's fine.
So those were all learning features or learning aids that are built into the multimedia. But multimedia itself enhances teacher and learning. At one time, somebody said, tell me and I will learn 45%. Show me and I'll learn 75%. So how did multimedia help? Well, first of all, we showed lots of stunning, beautiful pictures that capture science phenomena. And a picture is worth 1,000 words. Primates, after all, are pre-adapted to be visual. They take in a lot of data through images, and we're bred to do that. It uses intriguing images from science to delight the senses. Beautiful pictures focus the mind and command attention. They distill key points that are easily remembered. They make complex ideas simple and clear in a human-oriented delivery. We also used at-a-glance learning feature, all information in one place. And after all, some people learn best by pictures, some by sounds. And look at these pictures. Aren't they beautiful? Stunning pictures of science phenomena. Um, they can ask questions at each step. This one is one of our montages that puts a comet, an asteroid, a moon, and a planet together in a solar system picture. This is a picture of one of the fractals. This is a montage of patterns in nature, all kinds of patterns. This one showed that we even did it at three-dimensionality. In this one, actually, you guys looking at the screen right now, if you can look cross-eyed at this picture down in the left bottom corner, you'll see a protein wrapped around a DNA molecule, and you'll see it in 3 dimensions. And we taught the students to do that with various pictures because there's a lot of 3D stereos out there now. So stunning pictures, beautiful in color and so on, and also allowed us to see pictures of science phenomena that were very recent. This one was one that was just done on the Hubble telescope. It's really a montage of several pictures, and it shows the beginnings of stars in a gaseous cloud way far away from Earth. I might say that there are better pictures of that now, but we could include them. Animations show science phenomena in action that a person can't see. Like, remember we did the hierarchy of muscle, and we went down to the actin-myosin level? Well, these are 3 animations that happen at the same time. They show the myosin going and attaching to the actin and pulling it, and when that does it, it pulls the extremes of the muscle together, and it causes contraction of the muscle, which is just like what happens when your whole muscle contracts. Now, you couldn't see that, and that was 4 or 5 different levels of hierarchy shown at the same time and simultaneously for them to learn this. So see things how they happen in nature, show dynamic processes. Look and think about this for systems. You can't see this dynamics of systems many times, but here you are. Many science processes are too fast or too slow to be seen, like the movement of continents. And so we're going to show you in later animations how they can be sped up. And we also did fly-throughs where you had a cell and you could actually go into the cell and then see the organelles in situ, in place, and then click on any organelle and find out what it was about. So this gave them a feeling of control as well as a feeling of exploration. 14 experiments in higher education showed consistently that high multimedia interactivity was more effective than passive. I've told you that before, but this is this teaching and learning methodology of actually seeing things. And we did this for stars, where you can go inside a planet or inside your brain, all controlled by the fly-throughs. But we didn't finish all of those because, you know, we only had so much money from NSF. This is an at-a-glance graphic. It shows all of the levels of hierarchy from electrons, electron fields, and quarks and leptons, all the way up through the biological levels, ecosystems, into planetary systems, stellar systems, clusters of stars, galaxies, clusters of galaxies, clusters of clusters of galaxies, and then the wall. So 20 levels of natural system all at one time. And we use this actually, they could click on any one of these and find out why it was one of the hierarchical levels. And that's at a glance. You see the whole universe at a glance. In this particular one, we did time travel. Right. So I had the students make this up, and we had it in a loop, and we had faces appear at different times. And on the side, years would appear. So when we did the history of the scientific method, or geologic history in terms of the periods and the epochs and the eras, it showed how much time would have to travel for them. That gives them a perspective or a feeling about time travel. We'll see that later on. In this particular one, we were showing the evolution of the forelimb to the front leg of a horse. Unfortunately, it's not shown here. This is one of my test versions. I don't know if I can even recover the one that shows the evolution of the forelimb of an early mammal to the horse limb. This was my test to do that. And on the side would be the number of years and the number of mutations that people suggested would have to happen. And remember, I said by interactivity, you increase awareness, and this is good for this at-a-glance one. I already went over this one, so I'm going to skip it. Remember, the sequence is not determined, so they could start at the bottom, the smallest things, and go to the largest things in the universe, or they could start just the biological ones if they wanted. That's up to them. It's just so they do all of them eventually. Student follows their own interests, and that shows why there's so many different pathways possible. This is, we had some beautiful pictures from really, I think, a New York museum exhibit and again, there's choices. So for every period here, this one is the Cambrian. This is what the world looked like in the Cambrian. You could compare it with the Devonian or the Triassic. This is the period of the dinosaurs and so on. And this was all in the ocean. And some of these, only around the Devonian did we get out of the ocean. It gives them a feeling and again, control. They can pick to go forward or backward or recycle the thing or pick any of these periods and it would show a period. This is just the Cambrian, but we have pictures of the Permian and the Cretaceous and the Tertiary and Quaternary. There are other interactivities that occur. For example, in this case, the periodic table. They could actually click on any one of these, like they click here on iron. What is iron? Right there. They clicked on it and it showed them this. It shows the detail on iron, but you could have done that for one of the non-interactive gases here or any of the particular elements, other elements. In this one, they actually did experiments. Sorry. They could pull iron into the test box and see whether it conducts electricity or not. In this way, they could test every element in the periodic table interactively themselves and find out where the metals were and where the metals weren't. Isn't that neat? Here's the fly-throughs. You're going into a cell and you could pick the mitochondria or you could pick the nucleus or the nuclear pore and get information on it. Fly-throughs. You could see what is impossible to see. Like, look at this one. It's 18,000 years ago. There was, at the end of the Ice Age. But look at what happened. 13, 12, 11, 10, 8,000 years ago, much of the Ice Age had changed. And you can go backwards and forwards on that particular picture. In this one, things impossible to see, like the condensation of gases, cosmic gases, into a star, our star, and then when it gets to be a red giant and it eliminates us, and then it becomes a white dwarf, and then a black hole. So that's something, this took thousands of years. This takes billions of years, and normally we couldn't see it. It's from scientific experiments that have taught us how to think about these things in terms of time. But then there were trademarkable features. In addition to the learning aids that were built in and the multimedia features, there were trademarkable ones like the Cube Companion, the InfoNet Traveler, the Time Tunnel I've shown you already, virtual zools. I'm going to show you virtual interviews. And these other ones are here. There were more than one. For example, we decided to simplify the controls like forward or backward or repeat or get more detail, things like that. We decided that we needed lots of controls, so we invented the command cube. This is a graphic icon which does navigation for the student. It's the student control. And we decided that we would use a cube because every side had 9 various commands, and there were 6 sides, so you could get 54 commands in one very compact area. We came up with this in the 80s. And we said we were going to design a cardboard model that we could hand out so that they could bring it around with them and they would remember the various commands. So it was very compact and movable, as I'll show you in the next slide. And we allowed it to have a personality. Later, we found the same idea in the third book of Michael Crichton's series on Jurassic Park. They used that as a command device in that third book. But that was way after we had done ours. So it was an independent discovery, or we haven't even implemented it yet. We plan to have it have several different personalities. You could pick at the very beginning as a student whether it was going to be helpful, forgiving, and mild, or whether it was going to be aggressive and demanding of you, or whether it was going to be pushy for more detail and haughty about the material, or whether it was going to be comedic, joking, finding of ironies and materials. And its movements and its personality would be maintained throughout the rest. Okay, so this is a very long one, which begins to show some of the sides, and I'm going to speak over it, and I'm not going to spend much time on it because it's going to take a lot of time to finish, okay? But we never implemented this except for these visuals because the money ran out, and also because AuthorWare Professional was taken away from us, and we had to spend much of the time converting what we did in AuthorWare Professional and the modules to the Java program. I had a student programmer do that for a long time. So let's stop this. So you can see 9 by 6, each one with a different icon. Peter and Helene Finidori would love that icons. And it was also movable and had different personalities. So it could move around on the screen and the student had control of its personality and so on. Also, another trademarkable feature was virtual interviews. We decided that we would interview some of the statues of the oldest scientists in the world. And so we designed so that they looked like they were speaking. And we would have a list of questions that could be asked by the student that were relative to the work that that particular scientist did. And therefore, they could interview the scientists that had been passed away for thousands of years. But we also did current ones. This was one of my students.
Is a degenerative muscle disease. It occurs on the gene occurs on the X chromosome. It is responsible for producing a protein that connects the actin filaments with the sarcolemma or muscle membrane. And I do not correctly produce that protein, so the muscle cell membrane tears much more easily since it isn't attached to the actin fiber.
One of my dear students was in a wheelchair all the time, and so we asked him some of these lists of questions, and he answered them.
People should act the same toward a person in a wheelchair that they would to anyone else who wasn't in a wheelchair. They should offer to help when it looks like the person in the wheelchair needs some help, but they should also not be too helpful because the person in the wheelchair might feel patronized.
So practical questions and fundamental bio questions. Remember, they learned about actin already in the hierarchy, or things about the history of science in the virtual interviews. We also designed a traveler that they could get into, that would allow them to sample the species brain. And we would tell them that, in fact, the ISGE curriculum for the whole year was a sampling of the species brain in terms of science. And so they had the idea that they had a thing they could travel in, and they could actually go into it and look at structure, or they could look at mathematics, or in other words, they had different things, that different stations they could go to where the information traveler would look at the species brain. And so the species brain we talked about as a metaphor, where you could go through and these laser beams were sampling the species brain, which of course doesn't exist, but it was a good idea. Then we used metaphors to capture in pictures, like the species brain we just showed. But what about the transfer across generations? where this was an actual picture from our modules that we created, where basically we transfer what we know from generation to generation. And when a person dies, their neural nets are gone, and that becomes a problem for the whole species. So the species brain has a bunch of shared neural nets, and that's what things were going through. The ISGE was going through. And then data that is not in current science we could do. Like this one is one from my systems allometry work, where I compare planets, stars, clusters of stars, and clusters of galaxies. And in essence, we look at means of mass dimensions versus means of linear dimensions, and you come up with an equation, an allometric equation that has a probability of less than 0.001, which is very significant. That data isn't in the literature yet, so we had new things in our science. Whoops. I'm getting toward the end of this talk, so this is great. I think I'm going to be able to finish it easily within 2 hours and even have questions. And here's other things that you can't see. This is an artist's interpretation of going through our galaxy and finding a black hole with its event horizon circling around it. In the current literature, this is a reconstructed visualization of something we can't actually see at all. But then there's other things that can't be seen that we used science for. For example, if you're a three-dimensional person, you have a Z as well as an X and a Y axis that you're aware of. You're not living in a plane. And so you could see a line going through your current thing. But what if you were a two-dimensional person? This is what you would see. Instead of seeing the line go through, you would see a dot traveling through a space. Could you visualize a line if you were a two-dimensional person? And we did this the same for a sphere going through a two-dimensional plane. This is what you would see. Could you imagine a sphere from just seeing this? And that's fascinating. And then, of course, we did it with other objects like the cube. This is what they would see when a cube goes through. Much harder to visualize. And then what we did is we gave them a picture of a hypercube and said, okay, this is a four-dimensional object going through your three-dimensional space. What does it really look like? And oh man, did they get fascinated with that sort of stuff. We also had transdisciplinary labs. This one is a comparison of hierarchies across the human being down to the tissue and cell level, down to the DNA level and through the organelles, and then things in geology, and then things in terms of chemistry, and then we even took a computer apart to show that it's hierarchically based. So this was the lab that went with the hierarchy modules, 12 levels from human to geological to atomic to computers that were shown in the interdisciplinary lab. So traditional science labs are restricted to one discipline and usually one phenomena, but the transdisciplinary lab at ISGE has 3 to 5 disciplines in each one. The lab times are open schedule. We actually had a lab for this. The one I showed you there was just the one side of the lab. We had computers on the other side. Now we don't have to have computers. The hierarchy lab is just shown across 7 sciences. But in another we did in the chaos lab, the students actually took their own heartbeat and showed that it was chaotic rather than regular. And in fact, when you have a regular heartbeat, it's fibrillation and it leads to death. It's something that they were amazed at because they think their heartbeat is regular because they're not looking at it in detail. Data collection and analysis were required in these labs, and so it met the scientific qualifications that are necessary by the science disciplines in order to satisfy the science GE. Very important. But the most incredible thing is that thing I showed you earlier about music and computer programs having the same hierarchical structure as genetics and the structure of other things. Remember, I showed you this picture, but this is the animation that I built on it. I built this myself. It's the ATP molecule morphing into the first coin. And what I explained to the students is that when cells got complex enough that they needed something to interchange for the metabolism, they evolved the ATP molecule, which can transfer its energy. And I should say, for information, they evolved the GTP molecule. Similarly, when economics and trade got complex enough, we had to invent something to do as exchange. And what we invented was this, one of the first coins known to humans. Uh, just a great mind expanding thing. Okay? And then there were lots of numerous case studies. I think I beat that to death, so I'm not going to talk about it. But here's origins in 3 different disciplines: the origin of stars, the origin of higher elements, and the origin of cells. We did a lot in that too. In fact, that is the next long talk that I'm going to be giving for Peter that we will make into YouTube so it can be maximally applied. These were the actual modules that we finished for ISGE. We did the course philosophy and then all the case studies across hierarchies in the various fields, and then one of the scientific method one, well actually 2 of them, and then we started the cycle ones before we used up the funding. And so now I can't get it to advance. And when you clicked on any one of those, you access the actual modules for it. And so we went through lots of case studies in astronomy, lots of case studies in physics and chemistry. In our demo of ISGE, when it was live, I could click on any one of these checks and come up with a number of slides that showed the module for examples of cycles and oscillation in astronomy, or examples of feedback in astronomy. There's a lot more now, incidentally. And so we had 41 phenomena that we studied in geology. So when you brought this to the faculty and said, okay, they're going to get all of these phenomena across all of these isomorphies, they would be convinced that it would be a good course of study for science. This is the one that I haven't finished yet on fractals, and you can see it's an examination of one I had before. There's biology of trees, the physics of electrical discharges, the geology of river drainages, certain chemical oscillatory interactions. In computer science, the modeling of, I think it's a kidney. No, in this case it's a lung, and this is the kidney in biology. It's a supply of the venous supply for the kidney. And so we have all of these case studies, so we have a lot of science we're going over, but we're going over it in this unified way. So we have accomplished integration, like regulatory mechanisms. I could write essays on regulatory mechanisms in the universe of humanity. So we're about an hour and a half. I'm just going to finish up. There's a couple more slides here that are very practical. Is it possible to think of developing ISGE? The costs are extremely low, and so it's very competitive. But the modules are extremely high. Development of 1-hour interactive multimedia modules, we estimated costs in excess of $50,000. However, using the student mechanism I did, it was less than $10,000, which is only 20% of the industry cost for these computer games that you see now. Virtually all the costs are in development because the production is extremely cheap, because you just, what do you call it? Copy the programs. Whoops, sorry. At one time, we were going to distribute as a library of DVD-ROMs, but you don't even have to do that now because there's internet distribution. It costs even less. So the production cost for a year-long course was less than $10 per student purchase, while the profit would be much more, of course, for offering the courses. I had 17 CSU presidents respond to my president that said they wanted the ISG program at their campuses. None of that happened except at our campus. What about marketing? Market expansion projections show that multimedia should exceed $30 billion by 1998. I haven't gone back and looked at these. These were predictions in the 90s when I was going for the second NSF project support. The compounded annual growth rate was 82%. The multimedia PCs were supposed to go up from about 5 to 13 million. CD-ROM drives were going to go up. All of these are included nowadays in the standard home laptop. Home education software was projected to go up by 128%. It was supposed to be worth 90 million or so by the mid-90s. They projected an 888 million educational software business. I don't see the training market was to go to 4.3 billion industry by 1998. So marketing was pretty good. But let's look at this ISGE specifically, because it's not really training software and it's not really educational software per se. Well, one thing to look at is you have identify and targeted market that turns over. It's basically all 2- and 4-year college students. And non-science students are about 90% of the college students. So it's a captured market, much different from the market you have to attract for games. It's a renewable market because the students keep coming through, right? The annual freshman class is in excess of 2 million in the US alone, and that has gone up since the 90s. These slides were made in the 90s. So we're expecting a baby boomlet and a tidal wave, which did happen in the late 90s. So California University students are now closer to 450,000 students. When I made this site, it was 325,000. But actually, in most of the things, it says about 500,000 students. I talked about the letters from 17 presidents. But if you look at the community college system that could maybe even better use ISG, it has 180 campuses, and that's just a California one. Nationwide community colleges, there's 5.3 million students. So there's a huge market. And we were going to go to the California system and then the Florida and the Texas system because they're big. But remember, it's a renewable market. And if you estimate that you charge a student $100 per year for all of these modules, that's less than the textbooks for each semester or quarter. So it's less than the cost of the textbooks for 4 courses, and the profit margin would be very high once you got the development done. So it looked like a profit margin was in millions of students. And remember, we said this is 500,000 now. But then if you look at New York and you look at teacher training and 2-year and secondary schools and 4-year schools, there's a huge market for this program and the feeder populations. And then the spin-off projects, we have the 12 trademarkable features. We have the Knowledge Mapper program. And industry training could be using this too. In fact, I didn't give you the evaluations on industry, but I presented this to the corporate advisory board for the president, President Suzuki at one time, and we could not find the record of that, but they told me in person, why didn't I learn science this way? Why wasn't this possible? I want my child to learn science this way. But there are conclusions and problems. There are 9 caveats that I have here. And to be honest, one should include negative evidence. After all, ISG did not become part of the regular program at several universities. Why? Was it because of the student stress levels to learn so much? The copyright release problem is huge, and we can talk about that in questions if you want. Achieving adequate student flow, the students have to ask for it. There has to be a feeder population. But if they don't even know it exists, except in the departments, then they don't know what things that beyond basic biology exist. Then there's intellectual property rights and the MOUs, the graphic artist person power, the cost of programmers. One of the biggest problems is the faculty senates. Every time this is offered, it has to be approved by a faculty senate somewhere. And faculty don't like to take materials from someone else. They like their students to think that it was their material. And so it's tough to get voted into GE program by academic senates. It was the academic senate that killed it at Cal Poly, but that was because of power jealousies between the president and some of the people who were leading the faculty senate. I might say that when it went before the GE committee, it passed unanimously for the university. But there still are those caveats. Now, I'm not going to get into systems education 2, which is this San Diego University of California Frontiers of Science course that was offered in 1986, because I'm going to do that next time. And I'm going to stop sharing the screen. Is that okay, Peter? Could you appear?
Sure,
Peter?
I will. Yep, I'm here. Yep, very good.
You recorded all this stuff? Wow.
Yep. Let's stop the recording now. Thank you, Len.
Okay.